Neutron is a 13-ton class reusable launch vehicle capable of launching the mega constellations of tomorrow, here to support national security, and eventually launch our own satellites to space.
The question is always asked, well, how come you built Neutron? The customers that we currently fly on Electron said to us, look, we're all moving into mega constellations, so we need alternatives. And having some competition in that market space is really important, not just for our commercial customers, but for our government customers.
America needs an alternative launcher. There are a number of satellites now being developed into constellations that require launch as soon as possible. National security needs it, and we have a growing need for more and more space applications that require a ride to space.
If you stand Neutron up beside every other rocket that's been built and flown, it looks different. And that's fundamentally because we're able to start with a clean sheet of paper and stand back and go, okay, let's take all of the things we learned from our reusability program in Electron, all of the things that we learned from others' reusability programs, lay down a blank sheet of paper and let's start from scratch and design the optimum medium-class reusable launch vehicle.
So rockets are very beautifully engineered machines. There's a lot of cost, complexity that goes into developing a system that has to be so precise and reliable. It would be a shame to throw it away. So reusability on Neutron spans the entire vehicle. We have a fully reusable first stage that includes what we call the hungry hippo fairing that stays attached to the rest of the stage 1 structure. That allows us to bring the whole assembly back. So bringing it back as one piece makes this whole operation very airplane-like.
The vast majority of the structures on Neutron are carbon fiber composites. It will be the largest carbon fiber structure to ever fly when completed, which is incredibly impressive. There's a reason why all of the modern fighter jets ever made are carbon fiber. It's because of that strength and stiffness per unit weight. For our customer base, the reason why it's important is that will reduce fundamentally the launch cost as we go into repeat operations. The manufacturing process with the carbon fiber composites uses an automated fiber placement machine. The machine is 5 stories tall and has a powerful laser at its head. And what it does is it takes 16 spools of 1/2-inch tape. The tape is carbon fiber pre-impregnated with resin and pulls it into the head and depositions it onto the surface of the tool. This then creates a structure layer by layer, putting down something like a 1/2 metric ton of material a day.
One of the key challenges when you're designing anything for a rocket like Neutron is that there is not a lot of margin on either side of the design. Unlike maybe a bridge or a skyscraper, every pound or kilogram of mass that you add to a rocket design impacts directly the performance. And so there's a very fine balance between adding structure and keeping everything light. We've done a good job of that with Neutron.
Avionics is just an aerospace term for electronics which fly. It includes power systems, computers, data connections, navigation, radio connections to the ground as well. Each stage on Neutron has its own flight computer, and this is the device which makes the decisions during flight. It's looking at sensors from across the vehicle, it's looking at where the vehicle is, whether everything is nominal, how it's performing. It's adjusting the engine to make sure that you've got the right thrust. It's adjusting the thrust vector so you're pointing in the right direction. So that's all part of the avionics system, and we deploy our software and algorithms onto that entire system. And we make sure that it's responding in the way we want to by testing before we fly. Something like the hardware in the loop facility behind me allows us to have a fully representative rocket, essentially in a server rack in a lab, so we can run simulated flights to orbit using real hardware and using software simulations as well. So when we work with our customers, we can make sure that we are flying their rocket, their payload, their mission, and we can do that thousands of times all the way through the relationship. That can start before we even start a contract, all the way to launch day as well, so that we're constantly refining, making sure there's no surprises on launch day, because it's all about mission success.
Archimedes is an aux-rich stage combustion engine. There are 9 of them on stage 1. The stage 1 engine is capable of 165,000 pounds of thrust, and on stage 2, it's capable of 200,000 pounds of thrust. A majority of the Archimedes components are made out of additive manufactured parts. We leverage a lot of the Rocket Lab experience in additive manufacturing that enables us more design freedom and fast iteration.
We really kind of pioneered additive manufacturing for space travel. The Rutherford engine was the first orbital 3D printed rocket engine ever produced. Since then, I think we've already flown over 600 of these engines. We've made well over 1,000 of them. So moving into Archimedes was, we could take a lot of lessons learned from that and instantly hit the ground running with the things that we knew we were going to have challenges with. So the good thing about bringing additive manufacturing into production is that it's very scalable. And then it all just comes down to efficiency gains in the process. Where can we start printing a little faster, shaving weight, doing all these things just to get the machines to spit parts out as quick as possible. So it's really easy to turn the knob when it's time to scale.
I think I tell people really simply, we test rocket engines, right? Our job is to take the Archimedes, run it through the test procedures necessary to be able to determine its performance, its design criteria, make sure it's meeting those and that it's been manufactured to tolerance. Our days start here with the engineering and technician teams going through daily checkouts. That'll be leak checks. Then we go through purge checks, make sure the engine's inert. Then we're ready to test the engines. On a good day, we could go run 5 or 6 hot fire tests a day. You go through design analysis processes, but you really don't know until you get to the test stand in real conditions, real propellant, real pressures. So you want to go through those. And what you might do, and what we've done here, there's a few different designs, and we'll make changes. We may be able to change part of the main injector on the engine and be able to put the engine back and test again. So we've done design validation of 2 or 3 pieces of hardware in a week that way to help the designers move forward.
Alright, TC1, that looks pretty solid. Gonna go ahead and arm facility.
Launch site diversity is incredibly important for the nation. That's why we're really excited to bring national security launch down to Wallops Island.
Launch Complex 3 is located on Virginia's eastern shore at NASA's Wallops Flight Facility. It's constructed on pile-supported foundations. We have over 5,000 cubic yards of concrete on site to pour the foundations. On the launch complex itself, in the center, you'll see a large steel structure. That's the launch mount with its supporting mechanisms that support, hold, and subsequently release Neutron. In addition to that, you'll see a number of buildings on site. Those are the launch equipment vaults that have all the controls and electrical equipment for both the ground and the launch vehicle itself. You'll see a variety of tanks. Those are the high-pressure gas and propellant storage farms that store and ultimately load Neutron with fuel and oxidizer ahead of test and launch.
And Launch Complex 3, looks a little different than most other orbital launch pads of a vehicle this class. We did that intentionally to reduce the amount of bespoke infrastructure that needs to be created to support this rocket. You'll see the pad is quite clean with its propellant farms supporting the main launch pad in itself, and that's really largely there to minimize the amount of infrastructure needed for rapid reuse.
The Rocket Lab team at LC3 is one of the best teams that I've ever worked with. The crew that we have here is world class.
It feels incredible watching it all come together. It feels incredible being part of a company that's in the pursuit of something really ambitious.
The fact that we've got what I think is the greatest team we could ever have, the smartest people, most passionate, hardest working group of people working these problems, gives me the confidence that we're gonna get there.
Neutron is critical to the future of Rocket Lab as an end-to-end space company. We're bringing a world first of a reusable launch vehicle to the market, and it's an amazing engineering feat.
So the thing that really excites me about how we're going to use Neutron is not just serving the nation with national security. It's things like human spaceflight, which of course is exciting for everybody. But for me personally, what really gets me excited is now I have multi-ton capability to go to other planets.